This is entitled Validation of Seismic Design Provisions for Diaphragms and the Assessment of Higher Mode Responses on Earthquake-Resistant Buildings. So Professor Tsampras from UCSD will be giving that presentation. A little background on this. So diaphragm provisions are in ASC 7, which is our sort of national standard for new buildings, and had been relatively unchanged for a long time. But in ASC 716, which is what people have been using, it's what's required by, say, the California Building Code right now, and actually will be in the upcoming California Building Code, which will change on January 1 still. That had a major addition to it called the alternative provisions, and it was based on a fairly substantial amount of research that was ATC managed and government funded. And that continued on to be in ASC 722. So Professor Tsampras and his colleagues are kind of studying how well that predicts results. And so definitely an important subject for practicing engineers, affects how we design the diaphragms and their connections to walls, collectors within them. So it has meaning for a large subset of buildings. So I look forward to the presentation, and I will turn it over to Professor Tsampras.
Well, thank you very much, Brad. I hope you can hear me and see my screen.
Yep, looks good.
Excellent. Well, thank you, everyone, and I'm glad to be here with you celebrating this anniversary of SMIP. My name is Georgios Tsampras. I'm an assistant professor at UC San Diego, and today I'll present the work we are doing with Carlos Franco Mayorga with the support of the California Strong Motion Instrumentation Program. The project objectives are essentially to validate the alternative design provisions that Brent already mentioned, utilizing the strong motion data that are available to us, and also look at deeper dive into the second mode and higher mode effects in the total dynamic response of buildings utilizing this data. And as a secondary objective, we would like to populate metadata that we found useful throughout this process, and they are not currently available within the Strong Motion database. So we start working on this project on March 23rd, and in the past 6 months, we have met with the building subcommittee. We submit the report, we received comments, and we consider those, and I'll discuss those as well. And today I'll give you an update on this ongoing project. So all the conclusions are not final. So a little bit about the motivation. So in conventional buildings, we expect the seismic-induced horizontal forces developing at its floor diaphragm level to be transferred through a seismic force-resisting system to the base of the building. In this case, I show an example, a structural wall building, where we expect to limit the first mode response by the formation of an inelastic flexural mechanism at the base. And there is no way by design to limit the higher mode responses. So here I saw a well-detailed connection between a flat slab and a core wall, where you see these number 9 bars are essentially collecting the seismic-induced inertial forces developing within the diaphragm and transfer them into the plane of the wall. So we typically design these connections to remain linear elastic, and we don't anticipate to dissipate seismic energy at these connections. However, during strong motions and due to the displacement compatibility between the floor diaphragms and the walls or other structural systems, we should expect some damage there. And in fact, these damages may lead even to collapse, total or partial collapse. And Past earthquakes have shown structures like precast parking structures collapsed during 1994 North earthquake, or tilt-up wall buildings. And more recently, in 2010-2011 Christchurch earthquake, we observed collapses related to failures in the load path that we transfer the seismic-induced forces from the diaphragms to the seismic force-resisting systems. So these are issues that in New Zealand are known for a long time, and researchers and practitioners have been working to solve them, and especially how to quantify these forces developing in diaphragms and take into account the higher mode effects. And this is not related, the issue is not only related to collapse, the issue also related to damage localized at the connection between the floors and other structural members. So as Brett mentioned, AAC 716 and also AAC 722 includes an alternative method to design diaphragms and allows us to take into account the second and higher mode responses that contribute to the total dynamic response of a building. And this method was developed considering experimental results and numerical simulations. So here there is an opportunity to validate further this method, which is already an improvement, by utilizing the data that are available in the strong motion data set. So I want to show a little bit about the database that we have. So there are several buildings that are actively monitored, and we have available already metadata associated with the type of building, the type of seismic force resisting system, how many channels or accelerometers are installed in this building, and so on. And also, if we look at the metadata, we can understand that the majority of the buildings are reinforced concrete buildings and steel buildings. And the majority of the buildings are between 2 to 5 or 6 stories high. Within this metadata, peak floor accelerations and peak crown accelerations are provided, so someone quickly could assess the amplification effects for each building that is actively monitored. So at this point, we can say that we can utilize this information in order to further validate the seismic design provisions that were introduced in ASC 716. And I want to take some time to describe briefly what are these provisions. Essentially, they give us a tool to compute the seismic-induced diaphragm design forces, FPX, by utilizing the tributary weight at each floor level and the design acceleration coefficient CPX. So the multiplication of the two results in an estimate of the seismic-induced horizontal forces, which is reduced by taking into account this reduction factor, which considers the global ductility of the diaphragm system. So if we look deeper into this process, essentially we need to determine the seismic force resisting system that we will designing, the building location and soil class, the risk category, and the number of stories. Then we can estimate the natural period, the fundamental period of the structure, and then compute other parameters like the design acceleration coefficients, the modal participation factors, and eventually the design acceleration coefficients for diaphragms. So here is a plot from ASC 7 where it shows, for instance, the distribution of these design acceleration coefficients that we use to design diaphragms over the height of the building. This is a normalized value. So you can see that the distribution is not linear over the height for buildings that have more than 3 stories, equal to 3 or more stories. And on the upper 20%, we have a steeper linear variation that essentially demonstrates that this method does take into account the contribution of second and higher mode responses, which are effectively affect mostly the upper 20% of the structure. Now I want to start looking a little bit into some of the parameters used to compute this design acceleration coefficient for diaphragms, which will help us also select some criteria to establish the set of the buildings that we will be using to do this validation within our workflow. So first I want to look into the number of stories. which essentially will affect the fundamental period of the structure. So as the number of stories increase, the period increases, and they will affect also our design spectral accelerations and the modal participation factors. So as you see here, if we plot the the design acceleration coefficient with respect to the normalized height of the building, as we increase the number of stories, the design acceleration coefficients generally decrease, and they reach a lower limit here. And this is actually expected because as we increase the number of stories, as we said, the period increases. So these design spectral accelerations do decrease, and also their variation decreases within that larger period range. So this is expected. However, one thing that it's worth notice is that the upper 20% of the height of the building, still we observe a significant amplification of the design acceleration coefficients, and this is because the higher mode responses are still significant. Now, if we look at parameters associated primarily with the seismic force resisting system, we can focus on the seismic response modification factor and the overstrength factor. That these are both parameters that affect the first mode response of the building. And first, looking the reduction factor, which takes into account the ductility capacity of each seismic force resisting system, we can see that as we increase the reduction factor, we expect a reduction in the design forces. However, if you see the slope here in the upper 20% does not really change. So this effect of the higher mode responses is, as expected, not affected by the change in the R factor. Similarly, looking into the overstrength factor, we affect the first mode response, and as we increase the overstrength factor, we also, as we expect, increase generally the demands, and we don't affect significantly the amplification due to the higher modes. Last, I want to look into the mode shape factor, which essentially tries to take into account how effective is a seismic force resisting system into reducing the higher mode, the second and higher mode contribution in the total dynamic response of the building. And here you can see that essentially for a mode shape factor equal to 0.3, the distribution of design acceleration coefficients is fairly constant, so we don't get significant amplification of the design acceleration coefficient in the upper 20%. And this reflects that a building, let's say, that uses a buckling strain brace frame as the seismic force resisting system is able to mitigate the higher mode responses. So all these things are reflected within this design code, and that makes it a very, I guess, an improved method in order to estimate the seismic design forces in floor diaphragms. So having these parameters in mind, I guess we can broaden our horizon and look at the criteria that we need to take into account while thinking the buildings that we will select in order to make our validation. So related to the structural response of buildings is obviously the date of the construction of a building, because that determines the structural detailing and also the design criteria that were selected at that time. The number of stories obviously determines the seismic response, the location, the seismic risk category, and obviously the seismic force resisting system. Now there are some additional criteria like how many channels or accelerometers we have installed in the building, and what is the spatial distribution of these channels. Do we have enough sensors within a floor plan, and are they well distributed over the height? Now the number of recorded earthquakes and the intensity of those earthquakes that a building station that we selected is also important, because we would like to have building stations with a larger number of earthquakes that have occurred during the period that this building was instrumented, and we would like to select buildings that have seen earthquakes that resulted into significant peak floor accelerations. And last, it would be nice to work with buildings that have been previously studied in a way, because that enhances the available metadata that we can work with. And considering the long history of the seismic utilization program, I think this is something that we need to take into account. So for this preliminary study up to this point, the past 6 months, we were able to come up with a subset of building stations and seismic events. And basically the criteria we selected for now were, we looked for buildings that were taller than 12 stories, with maximum peak floor acceleration greater than 0.2 g, and we would like them to belong within the California Geological Survey network, because this network typically provides more metadata related to the buildings. So this resulted into 14 building stations, which each building station may have more than one seismic event that met our requirements. So in this case, we have essentially 20 unique combinations of building stations with seismic events. So we call them analysis cases, and they are listed here. So as part of this project, we eventually hope to extend the scope and include more buildings that have different number of stories, and in order to better understand how the actual response of buildings is compared with the design provisions. So having a subset of buildings now led to the next step, which is developing actually a framework to do all the computations required to in the study. So we decided to use Python, which is an open source programming language, to develop a framework. And the first module that in this framework is a module that will allow us to compute the design acceleration coefficients. So essentially, we took the data and metadata already included in the strong motion database that is already available in public, and we tried to basically identify the parameters associated with the design procedure and append these parameters within the existing database. And having done that, we can develop a module where we actually can perform the computation of the design acceleration coefficients for all the building stations, including in the database. So this is an example of a plot associated with these computations. Now, having the design acceleration coefficients, this is basically solves one part of our procedure. The other, obviously, is the response of the selected building subjected to given earthquakes. So in our study up to this point, we decided to compare the design acceleration coefficient CPX with peak floor horizontal translational accelerations. So that means that we needed to actually try to compute a relatively accurate estimate of the location of the center of rigidity in order to decompose the horizontal translational components of the acceleration from the torsional components of the acceleration. And the location of the center of rigidity in a structure obviously depends on the distribution of the vertical elements of the seismic force resisting system, but also depends on the intensity of the ground motion that this building has been subjected in the past, because some nonlinearity may result into different differences in the location over the time. So that meant we had to have a way that within our workflow we were able to compute the location of the center of rigidity, and essentially we looked in the literature and we found that Safak and Celebi published a paper in Journal of Structural Engineering where we can have an estimate of the center of rigidity using acceleration data. The main assumption in this study was that at the center of rigidity, the horizontal translational motions are independent from the torsional motions. So I'll spend a little bit describing this procedure developed by Safak and Celebi, and we used it in our workflow. And essentially, this method already developed and says that we need to have at least 3 measurements of motions at 2 different locations. So these are, for instance, in this schematic, P and Q, the 2 locations, and we have a recording of motion in the X global direction and Y global direction at point P, and we have a motion recorded at the Y global direction at point Q. So with that, Safak and Celebi expressed the rigid body translations in the X and Y direction and the torsional rigid body motion. Now, the next step is actually compute the best estimate of the center of rigidity. And in this paper, you can find that in statistics, essentially, you can use the cross-correlation between the horizontal translation along x-axis with respect to the torsional rigid body motion. And this cross-correlation has to be 0 in order to get an estimate of the position of the x-coordinate of the center of rigidity. And the same for the y-coordinate, the cross-correlation of the y rigid body motion with respect to the torsional response has to be 0. However, Safak and Celebi stated that this is rarely possible when we work with real data. So they propose that instead of setting these to 0, we try to minimize these functions. And if we want to work in the frequency domain, they stated that we can use the coherence function, which is basically another statistic metric in the frequency domain. And in order to eliminate the issue of the different frequencies, they propose to minimize the area under the coherence function, which is basically the integration of the whole frequency range. And this method gives us an approximate estimate of the x and y coordinate at each floor level that we have enough information in a building. So we took that method and after we validated with some information provided by Dr. Celebi and his colleagues, and we implement that within our workflow. So we started again from where we left before, where we have our database that is basically the database from the strong motion instrumentation program plus the information related to the design acceleration coefficient. And then there is a module where we can compute the estimate of the center of rigidity, and we can expand this information to our existing database. This information more specifically includes the X and Y estimates of the center of rigidity for each floor that we have enough information, and for each ground motion, because as we said, the center of rigidity may change with respect to the ground motion that we have. And that allows us to eventually do a comparison by having the horizontal translational accelerations over the height of the building and compare them with the design acceleration coefficients. So this also gives us actually the opportunity to look the torsional response independently and the superposition of the two, which is something that we are interested to do in the future, and it's part of the higher mode effects. I want to show two examples here for implementing this procedure. It's analysis case 5, where we have a 20-story building subjected to the Northridge 1994 earthquake. This is a concrete tactile moment-resisting frame. And you can see here that by computing the coherence area, we can find where is it minimized and get a best estimate for the coordinate x of this, for the center of rigidity. We can do the same for the y coordinate, and then we can decompose the accelerations and compute the peak floor accelerations over the height in x and y direction and compare with the design acceleration coefficients. Another example is analysis case 10, 11, and 12, which is a 52-story building that has been subjected to 3 ground motions. And this, we assume that it's a concentrically braced frame. And the interesting thing here is that with this method, actually, you may observe some variations in the best estimate of the center of rigidity, which here, for instance, the Sierra Madre earthquake data resulted in a center of a position of X coordinate that is different than the computation that we do using the other 2 earthquakes. And that may imply some small nonlinearity that occurred during the Sierra Madre earthquake. So having this workflow so far, we are able basically to run the computation through all the buildings within the subset, which we are planning to expand later, and make a comparison. And the first comparison results that in the observation that the buildings that we have in this subset subjected to the ground motions that we have considered, they don't exceed generally the design coefficients. And this is true for various seismic force resisting systems that you can see here, except from these three analysis cases, 3, 13, and 14. And these three analysis cases are special in a sense that they include buildings that they have potentially vertical irregularities. And the already ACE 7 in the commentary states that buildings with vertical irregularities have to basically have a special treatment and more sophisticated analysis in order to have a best estimate of the design forces for the diaphragms. So this is consistent so far with what we've seen in this very early study. And here I just want to summarize and say that we have been developing this workflow, and so far we have a way to compute the design acceleration coefficients and the decomposed peak floor accelerations in the horizontal, translational, and torsional modes. And we haven't found yet a building that has been instrumented and subjected to relatively strong motions that has exceeded the design coefficients, except from those buildings that have vertical irregularities. And in the future, we will try to expand the number of buildings to account more number of floors and types of seismic force resisting systems. And also, based on suggestions from the meetings that we had with the building subcommittee, we will also look into comparing the design forces coming from the previously existing design method, which is based on section 1210.1, that does not take into account the higher mode effects. And with that, I would like to thank you for your attention, thank the California Strong Motion Instrumentation Program for the support, and also Dr. Celebi and Slider for their help with some data to validate their procedure. Thank you.
Thank you very much, Professor Tsampras. I don't actually see any comments yet in the log, so let me ask one myself. If you go back to the measured versus predicted, that one, those M over D ratios, I just want to make sure I'm understanding this. Mm-hmm. The measured values are from actual strong motion records. Is that correct?
This is correct.
So that's the numerator, and the denominator is what you would predict for what the design value in the building code would be at that site.
That is correct.
Right. Okay, so these earthquakes are small earthquakes, right? There aren't any design earthquakes in the subset. So wouldn't you always, unless something really odd is going on, wouldn't you always expect these values to be noticeably lower than 1 because you're not comparing apples to apples?
Yeah, that's exactly right. And also we don't even include the torsional induced accelerations. But so far we just wanted to compare the data because in the database, this is what we have available. So that's why we want to expand the database to account for more buildings that potentially have been subjected to stronger ground motions.
Yeah, I think you're not going to find too many. I mean, that's the classic problem that we have. What I would think you might want to consider is the reverse. You have the PGA of these recorded values, so you might want to scale down the design value to be sort of equivalent to as if it were in a smaller hazard zone, and then compare that with what was actually recorded. That might be a little closer to an apples to apples comparison. Obviously nonlinearity, plays a big part, and you won't capture that, but I think that's worth investigating.
No, this is a good point. We've been thinking ways and good metrics that we could potentially scale the data we have. Let's say within a period range, the fundamental period spectral acceleration or so on. But yeah, things, because of the nonlinearity, the forces that actually being recorded or the accelerations being recorded may be limited. So we will ignore that part if we do some scaling. So we try actively to find the best way that we will give justice to the results and use some type of scaling potentially.
I think another thing, you had a nice thorough discussion of what's available in the set, and then you indicated what your selection criteria were. And in the end, you've focused on sort of mid-rise to high-rise buildings where you would think there would be higher mode effect influence, but that's a small subset of the total population of the buildings out there, right? I mean, the majority of buildings aren't anywhere near this tall. So you might want to, think about as you go farther, picking smaller buildings. They certainly have higher mode effects, and even 12-10-1, the shape implied by the 12-10-1 provisions was intended to account for higher mode effects. That's why that's why it's not a triangle. It doesn't have the flipping effect at the top that the alternate procedures do, but it has a bigger one at the bottom. So that would be of broader interest, I think, to the practicing community if you captured some of those smaller buildings.
I agree. And so at this point, the past 6 months, we want to make sure that we have a relatively accurate workflow and validate all the steps along the way that we can easily expand by basically adding buildings of interest and run this computation. So this is why the number of buildings that we saw today is limited, because we are developing the workflow and then we will expand it and make sure that the results are correct. So we'll definitely do that and work with shorter buildings, let's say.
So we kind of hit the time limit. I don't see any additional questions, but let me thank you for a nice, clear presentation. Obviously a very organized approach that your folks are taking. So that looks good. And I wish you the best of luck as you keep going. So Dan, we'll turn it back to you.
Thank you.
Sure. Great. Thank you, Brett.